In this video I hope to discuss about the Dirac-Delta function. So we have two cases actually, because we have to consider 1D Dirac-Delta function and also the 3D Dirac-Delta function. So first of all, I'm going to start with the 1D Dirac-Delta function, and finally I will move to the 3D Dirac-Delta function. So now I have graphically represented the Dirac-Delta function. So this delta x, so delta x denotes the Dirac-Delta function. So it varies with the x actually, because since we are only considering the 1D Dirac-Delta function, so that means that the function varies only on the it depends only on the x. So when you graphically represent this Dirac-Delta function, you can see that this is just a narrow spike. So narrow spike with a area of 1. So this area can be when you integrate this area, you will find out that this area is equals to 1. Actually, this is a unit area. So now let's say that the that means that if we say the function is delta x, so this function has two values actually. One is 0 and the other one is not equals to 0. So this happens when and we can say that the other one is infinity. So so delta x equals 0 when x is not equals to 0. This happens when x is not equals to 0. What happens is that only in the, so this is the x equals 0 point. So when x equals 0, the delta function has a value. The delta function cannot be 0 when x is equals 0. So that means when x is equals 0, delta function has a value. And if we say that the function starts with the minus infinity and it goes to the plus infinity, so that means if we integrate this with minus infinity to plus infinity, that if we integrate the delta function, so we will get 1, because delta function has a value only when x equals 0, and other when x is not equals to 0, so that the delta function is going to be a 0 value. So now we have considered that the area of this delta function, this when you graphically represent this delta function, so you know that we have showed that we have told that we considered delta function with the area of 1. So that means if you integrate this delta function, so you should get 1 as the value. Technically this delta function, delta x is not always considered as a function, because in the mathematical way, in the mathematical literature, so we can say that this is a distribution, because only when x equals 0 there is a value for this delta function. So this can be considered as a distribution rather than a function. So okay, if you are considering fx is a ordinary function, then fx delta x is 0 everywhere except x equals 0, because you know that when x equals 0, this delta function has a value. When x is not equal 0, then the delta function has no value. That means the delta function is equals to 0. So that means if you take the combination of fx and delta x, that means this is going to be 0 when x is not equals to 0. So if you take the combination of if you take the product of fx and delta x, so this is going to be equal to f0, because only when x equals 0 we have a value for the delta x. So that means we can consider f0 delta x. So this is always true for the delta function. So for an example, if you are going to integrate minus infinity plus infinity fx dx, sorry, fx delta x, so this is going to be equal to minus infinity plus infinity f0 delta x dx. So that means this f0 is a constant, so that means you can get it out of this equation, and you can have minus infinity plus infinity delta x dx. So that means minus infinity plus infinity delta x dx means that the area of this spike, the area of this spike, so you know that area of this spike is equals to 1, so that means you can get the value for this integration. That means this is equals to f0. So this is a really important factor of Dirac-Delta function. This is actually a very important point in the Dirac-Delta function. Okay, right now you can see that this is the Dirac-Delta function when x equals 0. So now I'm going to shift this delta function into a different place. So that means we have this delta function when x equals a. So this Dirac-Delta function is going to be at x equals 0, x equals a. So that means we have the x equals a point. So that means when we have x minus a is equals 0. So my new delta function is going to be delta x minus a, and this x goes to minus infinity plus infinity. There's no matter in this x. So now the delta function is going to be delta x minus a. So this is really important. So you have a value for the delta function only when x equals a, and the other points, when you are considering the other points of x, so there is no value for the delta function. That means if you consider the delta function, it is 0 when x is not equals to a, and it has a value, so that we define as minus plus infinity, because there is a value for this delta function when x equals a. So the previously we saw that actually when x equals 0 there is a value for this delta function, but when it comes to shifting this delta function to a point of a, we have this delta function at x equals a. So that means it has a value, so the area should be equals to 1 when x equals a. That means if you integrate with minus infinity plus infinity, delta function is going to be delta x minus a dx. So this is going to be equals to 1. So if you consider fx as fx is an ordinary function, then like previously we did for this fx delta function, that delta function is delta x minus a. So this can be written as fa, because this delta function has a value only when x equals a. So that means delta x minus a. So this is fa. So now if you integrate this minus infinity plus infinity fx delta x minus a dx, so this is going to be equals fa minus infinity plus infinity delta x minus a dx. So this is going to be 1, and this can be derived as fa. So these are really important values when it comes to the Dirac-Delta functions. Okay, now I'm going to discuss about 3D Dirac-Delta function, because because you all know that when it comes to reality we have to deal with the 3 dimension. So it doesn't matter whether you learn 1 dimension, you have to go further to the 3 dimensions as well. So right now I am going to define the 3D Dirac-Delta function, or you can say 3D delta function as well. So in the one dimension, I have showed that the delta function as I have defined the delta function as delta x. This is only when if you have a one dimension. So this is one dimension. But when it comes to 3D dimension, 3 dimensions, you have to use delta cube with the r vector. So this is in the r vector format. So this is in the vector format. So that means you have cube. So that means if you have x, y, z coordinates, that means you have a delta function of x, delta function of y, delta function of z. So this is the definition, this is the basic definition of the Dirac-Delta function of 3 dimension. And this r vector can be represented with x hat, y hat, and z hat. Okay, now if we consider x, y, z, we have let's say we have the x, y, z are the variables. So when this x, y, z equals x equals when x equals 0, y equals 0, and z equals 0. So previously we saw that the when x equals 0, delta function has a value. So now we are going to extend this delta function into 3 dimension. So that means these x and y and z should be equals to 0 in order to have a value for the delta function. If one of these are not equals to 0, that means let's say that if x equals 0 and y equals 0 but z is equals 1, so that means this delta function has no value for value when this kind of condition satisfied. So when only when x equals 0, y equals 0, and z is equals 0, delta function has a value. So that means if you have let's say that the delta function is going to be delta cube r. So this has a value. This has a value only when x equals 0, y equals 0, and z is equals 0. Otherwise it would be 0. So okay, now we have three delta functions, because delta x, delta y, delta z. So that means if you integrate these 3 delta functions with respect to x, y, z, if you integrate these delta functions with respect to x, y, z, that means you have to integrate 3 times. That means you have dx here, dy here, and dz here. So that means this is a triple integral. So this can be written as delta r d tau. So d tau is the volume element. So now this d tau can be written as dx, dy, dz. This is how we get this kind of a relationship. So now this is tau, because we are considering a volume here. So now we have this minus infinity plus infinity, because we are considering delta x dx. So that means delta x dx means this goes to minus infinity plus infinity, the range between the range of the function. So the range of the function is minus infinity plus infinity. This is true for all delta x dx and delta y dy and delta z dz. So now when you integrate this one, you will get the value of 1, because you are considering a unit value. Actually if you draw the, I'm not going to draw actual function. So if you have this kind of function, this should be a spike. So in this 3D motion we have this kind of function. So when you integrate this, you should get the value of 1. So this is in the Cartesian coordinate system. So when you have a other kind of coordinate system, you should know how to get this volume element, and you should know how to get this delta function, because I have shown you how can we derive the expression when using the Cartesian coordinate system. But if you have other kind of coordinates like spherical polar coordinates, you have to use the volume element for the spherical polar coordinates. Like for the spherical polar coordinates, the volume element will be infinitesimal volume element will be r squared sine theta dr d theta d psi. So these are the values of d tau when in the spherical polar coordinates. Okay, now let's say that if you have a function called fr, and this function is shifted to the point of a, not just a point, it's just a vector. So let's say that the delta function is moved to shift to a vector called a. So that means we have to use this notation. So fr times delta cube r minus a. These are vectors actually. In previously we have used the point, so this is not a point, this is a vector. So now we can say that only when r is equals a, we have a value for the delta function. That means you have to use f a and delta cube r minus a. So this is true for all kind of 3D delta functions. Now if you integrate fr delta cube r minus a with the volume element, so you will get the value of f a. And there is another definition for you. If you are going to find the divergence of r, so this can be divergence of r vector divided by r. So this magnitude of r, this r represents the magnitude of r vector, and we can see that this is equals to 4 delta cube r delta function in the 3D delta function actually. So now we can see that you know that from the previous videos you can write this r vector as I'm really sorry, I made a mistake here. So this should be r hat r square. So this is going to be equals to 4 delta cube r vector. So now this thing should be remembered. So this can be applied for the examples that we are going to consider. Okay, now there is an example for you to try. So evaluate the integral of I is equals integration of volume. So this is a volume integral. So r squared plus 3 times del times the del operator dot product is actually the divergence of r unit vector divided by r squared. So this is the infinitesimal volume element. So now where this mu is a sphere of is actually mu is represents a sphere of radius r centered at origin. So now I'm going to do this example. So now we have I is equals r squared plus 3 divergence of r hat divided by r squared d tau. D tau is the volume element. So now we know that this is going to be my R function. So this is going to be my function, ordinary function. So now we have another term here, so you can replace this term with the 4 phi delta cube r. So since the sphere of radius r centered at origin, so this mu represents a sphere of radius r centered at origin. That means if you draw a sphere, the center is at the origin, so that means 0 0 0. So that means the spike, our delta function is going to have a value at the origin. So that means only x equals 0, y is equals 0, and c equals 0. So only when this happens, we have a value for the function, delta function. So now I have seen that f r 4 phi delta cube r. So this can be written as you can take out the 4 phi out of this equation, and we have this mu sign here, and we have this r squared plus 3, and you have this delta cube r. Now you can see that this is f r, and you have a delta function here. So now you are going to use this previous result f r. If you have this f r delta cube r, you can use f0 delta cube r, because only when r vector is 0, r vector is a null, you can get a value for this delta function. When if r vector is not equals to 0, then delta function has no value. Delta function is not equals to it's going to be 0. So that means you have to consider f0 here. So that means you have to put the value of f0 here. So that means if 0 means you have to calculate that one, theta. So now we are going to calculate the f0. f0 means you have to put the r is equals 0 to this value, to this function. So that means you have 0 squared plus 3. That means f0 is equals to 3. So now you have 4 5, and you can consider this as a constant. So you can get this out of this integral, and you have this mu sign and the delta cube r. So this is a volume integral. So now you know that the volume integral, this can be represented as 1. So the value of this volume integral is going to be 1. So that means you have 4 5 times 3 means 12 5, and the answer will be 12 5.